Let's see, we've got Julian with us and Braxton. That's good. And let's see who else we've got. We've got, we got a good crowd. We've got Alex and Muhammad, Taylor, Braxton, Nathan. Yes, good going. We got a good crowd. And there's Julian, Tyler, Reagan. Good deal. Okay, it's time to start. Any comments or questions before we launch into the study of our thermodynamic cycles? We started on it. What is today? Wednesday. We started on it Monday. Do you have any questions before we continue? Okay, well let's jump into these thermodynamic cycles. There's three different kinds, and I want you to draw the cycle schematic the way I do it. I like it better than the way the book does it. But there's three different kinds. There's the heat engine. There's the refrigeration cycle. And then the heat engine cycle, the refrigeration cycle, and the heat pump cycle. Now the heat engine cycle has another name. You'll see it referred to as the power cycle, because the purpose of the heat engine or the power cycle is to provide power. That's why they have them, so they can provide you with power. Now the purpose of the refrigeration cycle is to cool off your hot dogs or your milk or whatever you want to keep cool, or your car or your home if you got air conditioning. The purpose of a heat pump cycle is to warm up your house in the winter. You want to try to keep warm. So they all have different purposes. So let's do them one at a time. Talk about the heat engine cycle, unless you have a comment or question. Okay. Well, what I want you to do is to draw this schematic. Like this. Heat engine cycle is it's got a clockwise schematic. It goes around and around clockwise. It has a low temperature and a high temperature. And it has a power output. It has a heat transfer term at the lower temperature and a heat transfer. Well, I'm writing them as rates. That's a heat transfer rate at the lower temperature, and that's a heat transfer rate at the higher temperature. And this is your power. Draw the schematic like that for me, please, for the heat engine. Now they have an efficiency. Heat engines have efficiency. And it's something you desire, namely the power. That's why you have it. You want to provide power, and then you divide by something that costs usually money. It's going to cost you money to buy the fuel for the heat engine. Now, according to the first law of thermodynamics, that power has to equal the difference in the heat transfer rates. So you can write the efficiency like that. Now, you got to understand now, this is the actual efficiency. There's another efficiency that's the maximum theoretical efficiency if the thing ran perfect. If it didn't have any, what they call irreversibilities. There's a section in your chapter about reversible versus irreversible processes. And I can talk about those with you. Friction, for instance, causes you to lose efficiency. If you had no friction at all, you would have a higher efficiency. There are a number of things that can cause a lower efficiency. One is heat transfer from vastly different temperatures, from something that's really hot to something that's cold. Of course, you'll have a heat transfer, but you'll lose some efficiency because of the big heat, the big temperature difference. There's a bunch of other things. It's in your chapter. But there's a maximum possible efficiency, and it's based on the Kelvin temperatures, and it goes like this. And in fact, the Kelvin temperature scale theoretically is based on a perfect power cycle that runs without any irreversibilities. And I want to warn you, there are no perfect engines. The car engine sadly only gets somewhere around 20 to 30% efficiency. So for every dollar's worth of gas, you're getting 25 cents worth of power. But some cars are more efficient than others. And they have a maximum possible efficiency based on the Kelvin temperatures. Well, there you have it. There's your facts for the heat engine. And let's do a problem. Then we'll do the other two kind, the refrigeration cycle and the heat pump cycle. Now this first problem we're going to do is 531. So we're going to do 531. Let me find it here. A car engine burns 5 grams per second. I thought for a second that was 5 gallons per second, but man, that'd be pretty bad gas mileage, wouldn't it? 5 gallons per second. No, that's 5 grams per second at 1500 K. Well, here, let's label some of this stuff. I think that's the hot temperature, the 1500 K. Okay. There's your 1500 K. And and you've got an m dot of 5 grams per second. Let me write that down someplace. M dot equals 5 grams per second. Now I tell you where that's going to come in. See, QH dot is going to equal to M dot times little QH. That's how the units work. And see, they're giving us this. If we could figure out what that is the heat transfer per mass. If you could multiply, you could get the QH dot. Let me keep reading now. This is 531. It rejects energy to the radiator and exhaust at an average temperature of 750. Well, let's write that down. This is your low temperature. This is 750 Kelvin. There we go. The fuel provides 40,000 kilojoules per kilogram. Let me write that down. 40,000 kilojoules per kilogram. You might wonder, well, what is that? Well, here's why units are so important. I can tell what that is by the units. That's this guy right here. That's, you know what that is? That's little QH. It's the heat transfer per mass. See, look, kilojoules per kilogram. That's energy per mass. It's kilojoules per kilogram. So you know that's a little q. Become familiar with the units and you can figure this stuff out. What is the maximum power the engine can provide? Well, the maximum power, I think we could probably figure that out. Here's what they're after. They're after this W dot. If the thing ran, if it ran perfectly, then these would equal, guys. These would equal. Now, instead of using big letters, why don't we use little letters? Here's my plan. I'm going to use little QH minus little QL over little QH. You see the difference is just multiplying by your m dot, and that's given. So I think that's legal. And what we're going to do is we're going to set these equal. The thing is, we know what this is. This is 40. Here, let me write it out here. This is 40,000 kilojoules per kilogram minus QL over 40,000 kilojoules per kilogram. And we're going to set it equal to this. And we know this. See, this is 1,500 K minus 750 K all over 1,500 K. You see what I did? I set the actual efficiency equal to the maximum possible efficiency. And we're going to get this heat transfer per mass to the lower temperature. And from that, we might get lucky and be able to find the thing we want. Well, what we're after is this. Okay, well, I'm going to shut up for just a tiny minute, and I'm going to let you guys get your calculators out. Can you read my writing? I hope. And I want you to find this little QL. See, what we're going to do is we're going to find little QL, we're going to find little W, and we're going to find little QH. Go ahead, find this little QL, I'll be quiet. Well, I've got my little QL, okay. Let me go to one of my wonderful students here. Bryce, I haven't picked on you in a long time, Bryce. Have you got the little QL from this equation yet?
I believe so. I got 20,000.
That's what I got. So we think
Kilojoules per kilo.
here. We think this little QL is 20,000 kilojoules per kilogram. And now we can get the, well, I really want this big QL thing, I think. What do they want us to find? Just a minute, I got lost. Yeah, you know what? This is what they want. They want this power here. Okay. Well, here we go. Q L dot is going to equal your M dot times a little QL. And Bryce got the little QL right. He knows what it is. There it is. But now watch it. That M dot needs to be in kilograms. So write it as 0.005 kilograms per second times your 40,000. I don't have room. I'll just go QL there. And here goes. 0.005 times 20,000 is, I get 100. I just figured out this QL dot is 100 well, it's kilojoules per second. You know what that is? That's a kilowatt. So we think that's 100 kilowatts. Then what? Well, we already know this. We probably should write it though as QH dot. Let's do that. I don't think we have that. See, QH dot is going to be the M dot times the little QH. Well, let me do that. So take 40,000 times 0.005. I got 200, guys. This QH dot here is 200 kilowatts. Okay, 200 kilowatts come in, 100 comes out this way, and guess what this has to be? It has to be 100 kilowatts. This is a big engine, isn't it? And I think we're done. 531. What's the maximum? Yeah, we're done. The maximum power that this engine can supply is 100 kilowatts. That doesn't mean it's going to really supply that, because that's just the theoretical maximum. Do you understand? The actual power will be less. Remember, there's actual power and there's maximum possible power, but it kind of gives you an upper limit of what's possible. The biggest power that you could get is 100 kilowatts out of this engine. Okay, well, let's talk about refrigeration. Yeah, go ahead.
Yeah, this is Nathan. I'm confused why we set, well, basically in actual equal to in maximum when you did the little QH minus.
Okay, the reason why we did that, Nathan, is we want to find out the maximum possible. And see, the actual efficiency deals in heat transfers. The maximum possible deals in absolute temperatures. Now, if you set them equal, what you can find is the actual heat transfers going on, and we did. We found the heat transfer rate from the high temperature is 200 kilowatts. The power of this engine is 100 kilowatts. Now that is if it runs perfectly. And what this is the heat transfer rate to the environment. See, all power cycles heat up the environment. You burn fuel, you get some power out of them, you're able to do some work, but then you've got some exhaust and some heat that is no good to you. You're just heating up Oklahoma. But if you set them equal, you can get the maximum possible power that you can get out of that engine. Did that make sense?
I guess I didn't read the problem. It did ask for maximum. So
Yeah.
Okay.
Okay, well, let's do the refrigeration cycle. I'm going to say goodbye to this heat engine, or also called the power cycle, and we're going to do a refrigeration cycle. If it's okay with everybody, speak up now. Speak up now. Speak up now. It's too late. You didn't speak up. And now we're going to do a refrigeration cycle. The topic right now is a refrigeration cycle. Now here's how I want you to draw the schematic diagram for the refrigeration cycle. Draw it counterclockwise. Round and round she goes counterclockwise. Everything just sort of backwards. So you can put in little letters if you want. QH, this would be TH, TL, and this would be, now watch it, it's going the other way, it's a little w. I don't know whether we're using per mass values or per time values or what, but we'll find us a problem and do it. Here goes. Here's one. This is 535. It's a refrigeration cycle. Let me find it here. 535. Okay. A household freezer operates in a room at 20 degrees Celsius. Well, see, that would be this. That's the high temperature. 20 degrees Celsius. Now, why don't we go ahead and get the Kelvin? That's 293.15 Kelvin. There we go. So we got that figured out. Now keep reading. Right now we're doing problem 535. It's a refrigeration cycle. Heat must be transferred from the cold space at a rate of 2 kilowatts to maintain its temperature at minus 20. You know what this is? This is minus 20. It's a freezer. You got ice cream or something in there. And now the Kelvin would be 253.15 Kelvin. There we go. And something about heat must be transferred from the cold space. Well, you know what I think? I think they got the big, let's go with the big Q L dot here, because they're giving us that. And this is the big Q H dot, and this is the big W dot. They said that the heat must be transferred from the cold space at a rate of 2 kilowatts. Okay. To maintain its temperature, what is theoretically the smallest power motor required for the operation of this freezer? Okay. Well, we need to do, they don't call them efficiencies. See, efficiencies are always less than 1, but they call these betas. They're always bigger than 1, and they have a fancy name. They're called the coefficient of performance. It's called the coefficient of performance. And they just use a symbol, the Greek letter beta. Now, the thing is, there's 2 of these. There's a beta actual, and then there's a beta maximum possible, just like with the heat engines. The beta actual, it's kind of like efficiency. It's what you desire divided by what costs you. Well, what you desire is this here. What you desire is that QL dot. You want to remove heat energy from your hot dogs and your milk and so forth, ice cream. But see, you got to pay for it. Now, what you have to pay for it is you have to plug this thing in. If it's a freezer, you got to plug it in. That costs you money. See, there's a plug here. Look, see your plug? If you unplug that freezer or refrigerator, it doesn't work so good. That ice cream becomes pretty sloppy. I had a part of a beef years ago in my freezer, and I forget what happened, but several days went by. Oh, it was a disaster. It was a disaster. Beef doesn't keep good if you don't keep it refrigerated. Okay, and the maximum. And now, here's how I remember this. You can write this like this. According to the first law of thermodynamics, the amount of work done is equal to it's the algebraic sum of your heat transfers. Here, I'll write it for you up here. This is a form of the first law of thermodynamics, and it works for cycles. You got to have a cycle to write this equation, but we do. We have a cycle. And
Could you write that a little lower?
Say that again, please.
Could you write that a little lower?
Yeah. Did it go? Did it go off this? Yeah,
Perfect.
there we go. I hate to touch this thing. This is a touch screen computer, and man, if you have one of those and you touch it, sometimes it just, who knows what'll happen. Something bad happens. But I got lucky. I think we're okay. Now the maximum, it's according to your Kelvin temperatures, and it goes like this. Now these equations are all in your book. Let me show you. This would be chapter 5, right? Let me show you where these are. And you can find them in a hurry. Oh, I see a bunch of them here. On page 172. Yeah, there we go. Hey, I see that equation on page 172. You can see it too if you want. Okay, now here's what we're going to do. It's the same trick that we did last time. we're going to set these equal. We're going to set the actual coefficient of performance equal to the maximum coefficient of performance. We're doing problem 535. It's a refrigeration cycle. Well, it's a freezer actually, isn't it? Okay. Now they gave us this here. It's 2 kilowatts. Yeah, we know that. So I'm going to write the equation now. Here we go. There's some room right here. I might be able to get it in here. What we're going to do is we're going to set these two equal, but see, we know this. So what we have is 2 kilowatts divided by QH dot minus QL dot. No, we know what that is. We know it's 2 kilowatts. And see, we're going to set that equal to this. But see, we know what this is. This is 253.15 K. And then the difference is 40. The difference between these numbers, minus 20 and plus 20, is 40. Or you could subtract those and you could get 40 that way too. See, it cools off. How come that isn't a minus 40? Well, because it's not. It's a high minus the low. Yeah, that's it. It's 40. Okay, look at here. Hey, we have a lovely equation. Let me box it up for you. Nice equation with only one unknown. I'm going to shut up for a minute. I want you to find that heat transfer rate at the high temperature. Find it. I'll be quiet. Well, I got a value for the heat transfer rate at the high temperature. I wonder if that's what you guys got. Let me go to one of my excellent students here. See, I've already picked on Julian, I think. Taylor, I haven't picked on you all day. Taylor, unmute and say hi.
Hi.
Hey, Taylor, did you get this heat transfer rate at the high temperature yet?
I believe I did.
What'd you get?
2.32 kilowatts.
That's what I got. Okay, this here is, thanks to Taylor, it's 2.32 kilowatts. Okay, well, we can get W dot now, see? Two goes in, And what W dot has to be is 0.32 kilowatts. And see, when you add those two, you get 2.32 kilowatts. So we just found out what the power is. It's 0.32 kilowatts. And I think we're done. Isn't that what they wanted? Let me see. 535. Yeah, now that's the smallest power motor. Now you can get a bigger motor, and you would in an actual refrigerator. You need a little bigger motor than that because it's not going to run perfectly. But we figured out the power of our motor is going to be 0.32 kilowatts. Ta-da, we got that one under our belts. Any questions on that?
Yes, I'm sorry. I got the QH dot, but I missed your final step there.
Oh, yeah, here's the final step. Now you got the QH dot is 2.32 kilowatts. Now this is kind of like horses going into a barn. You got 2 horses going in this door. You got 0.32 horses going in this door. So how many horses go out this door? Well, 2.32. They just add up. That makes sense? I don't know about 0.32 horses. That's kind of goofy. But these are coming in, and that's going out. And the first law of thermodynamics says what goes in has to come out. You got it now?
So the answer is QL, 2 kilowatts.
Well, QL dot was given of 2 kilowatts. That was given.
Right.
What we found was 2.32. One of my excellent students found that. And so if you have the 2 and you have the 2.32, this has got to be 0.32 to add to the 2 to get the 2.32.
I got you now. Sorry about that.
All right. Yeah, good going. Okay, well, let's do the heat pump cycle now. I need to make enough room to do the heat pump cycle. Let me erase some of this stuff. Now I'm going to keep this diagram because the heat pump cycle looks just like the refrigeration cycle. The schematic is identical. It's just that the numbers are going to be different.
I have a question.
Okay. Yeah, go ahead.
My final answer was 0.411 because I see you find 0.3. I was trying to figure out what exactly I did wrong, but I don't know. Because
Oh, gee, I wish you would have spoken up before I erased that.
I had a problem
my-
with my microphone. I'm
Is
sorry.
that my friend Reagan?
Yes, this is Reagan.
Okay, well, Reagan, let me see if I can go back.
But it's fine. We can move on. I'll email you that. Maybe we
I
talk.
think you just made an arithmetic mistake is all.
Yeah, I hope so. Yeah.
Here's what we had, Reagan. We had 2 kilowatts over the QH dot minus the 2 kilowatts equals the TL, and the TL was 253.15. And this is the difference in the temperatures. This is the 293.15 minus the 253.15. This is what we had, Reagan. And when we solved this, what we got was 2.3. Well, what I got is 316. But what my excellent student got was 2.32. He just rounded off.
Yeah,
which
I
is
see
fine.
where I made a mistake because
Yeah, it's
I did
just an
two,
algebra thing, Reagan. I'm sure you
for
you just
3.15.
you just pushed the wrong number. But are you okay now?
Yes, I'm okay. Yeah, good. Thank you.
Good, excellent. But thanks for speaking up. That's what I'm here for. Now we're going to do the heat pump cycle. And we're going to do a problem. We're going to do problem, let me see if I can find it here. Heat pump cycle. Yeah, this is problem 528. Now here's the thing on the heat pump cycle. They have this beta, but they call it beta prime. It's the coefficient of performance of the heat pump cycle. And they have an actual, and they have a maximum possible. And the actual is equal to, well, you have to decide, well, what do you want? What is desired with a heat pump? Well, it's this. You want to heat your house. Here, let's put a roof on this house and maybe a door there and a window there. There you go. There's your house. You want to keep it warm in the winter. It's called a heat pump. And what is desired, what you want, is to have heat transfer to your house so you'll be warm in the winter. And this is equal to this divided by this. This is what you have to pay for. Again, you got to plug that in. It's not free. You're not going to keep your house warm in the winter free. Sorry, it's going to cost you money. But see, you could write this according to the first law of thermodynamics like this. So there's your actual. Now here's your maximum possible. It's based on the Kelvin temperatures. Okay, now let's read our problem. We're going to do problem 528. And we'll put in our numbers. I want you to draw this schematic. And you'll discover when you do these on a PV diagram, they go counterclockwise. You'll discover that. Your compressor's here, and this is your condenser. There's your expansion valve, and there's your evaporator. They go counterclockwise. And on this one here, you've got 4 megawatts of heat at 65. That's the cold temperature. This is not a house. This is some kind of industrial application. But you can have heat pumps besides trying to heat your house. But this is 65 degrees Celsius. But we need, and they said this is 4 megawatts. Now that's a lot of watts, guys. That's 4 million watts. Now we need the, add 273 to it. Did I do that right? 338. And it says here, it's to be delivered as the heat at 145. This is 145 degrees Celsius. Just a minute. Let me get the Kelvin here. You suppose I did that right? If I didn't, somebody jump on me because we got to have this right. And they want to know the minimum amount of power that you can run this heat pump. They want to know what the minimum is. Well, what you do is you set these equal. Here, let me put in our numbers. We don't know this, Bob, but we know this. It's 4 megawatts. And we know these. This here is, that's the 418, if I did that right. And that's 418 minus the 338. What's 65 from 145? I can't do that in my head. It's 80, isn't it? Yeah, this here will just be 80. When you subtract those, you'll get 80, right? Yeah, that's right. Okay, now we're going to set those equal. Here, let me write it out for you. We're going to write out our equation. Here we go. Now those are in megawatts. All right, there's your equation. I'm going to be quiet for a bit of hurry. We don't have much time left. See if you can solve that. Go ahead. See if you can solve that.
Hey, Mr. Griffin, I'm sorry, I have a question.
Yeah.
Where do you get the 80? On the BMax, you see the
Where do I get the N?
80, 80. Whenever you do 418 divided by 400.
He's asking where did you get the 80?
Oh, okay. Thank you for asking. Well, if you subtract 338 from 418, I think it's 80, isn't it? Did I do that right?
Because on that, I got like
Yeah.
5.22. I don't know if I did it wrong because
So subtract 338 from 418. I'm getting 80.
that's the truth. Okay, I got
Actually, what I did is I just subtracted 65 from 145. That's a lot easier for me. And I got 80. Okay, we're running out of time. Oh no, we're running out of time. But if you solve this for QH dot, here's what I got. I got 4.947 megawatts. Does that show up on the board there? 4.947 megawatts. That's supposed to be a 9. So we know this is 4.947 megawatts. And we know this is 4 megawatts. So I can tell you what this power is. You know what it has to be? It has to be 0.947 megawatts. Right? And that's the minimum power you can, in a real heat pump, you're going to have a power bigger than that. But that's the power that you'd have to have if this heat pump worked perfectly with no irreversibilities, which we will talk about soon. So there you have it. Enjoy your homework. It's on Blackboard. And
Professor, our class ends
Yes.
at 1:20.
That'll be
Oh,
1220.
thank you. Oh, wonderful. Thank you so much. I'm mixed up. I'm mixed up. It ends
1220,
at,
sorry, not 120.
yeah, it ends at 12. Hey, we got more time. How wonderful. Now, who was that? Who just helped
That
me
was
there?
Nicholas, sir.
Nicholas, you got a big fat thank you point. We're gonna put a big fat thank you point right there.
Hey, Professor,
And yes,
back to me. I'm not getting the same answer you got on the
okay.
wait.
Okay, well, here, let me do it. We got time. We got time now, thanks to Nicholas.
Because whenever I
uh,
do 418 divided by n subtract, I get 5.2.
Okay, here, I'm gonna do this now. I'm gonna do some algebra. And here's my equation, Reagan. And what I'm gonna do is I'm gonna go that times that, which is 418 QH dot minus 4 times 418, which I don't know what it is. Just a minute here. 4 times 418. I'm getting 1672 equals 80 QH dot. Now what I'm going to do is I'm going to subtract 80 from that. And here's what I get. 418 minus 80 is 338 QH dot equals 1672. Now I'm going to divide and I'm going to get QH dot. Here goes. All right, I'm dividing. And I'm getting 4.947 megawatts. Now, if you didn't get that answer, you're doing something wrong. And you know, a good time for finding out what it is you're doing wrong would be now, not later when you get to OSU or wherever you're going. I think you should find out whatever you're doing now. Did that answer your question?
Yes, it did. Thank you.
Good. You are so very welcome. Just ask. Okay, hey, we got time to talk about the Carnot cycle. Very important. If you're happy, I'm going to erase this. We've talked about all three cycles. Heat pump cycle, heat engine cycle, refrigeration cycle. It's in your chapter. All the equations are right there in your chapter 5. And I'm going to erase this. Last chance to say anything. Okay, goodbye. Problem 528. And the topic right now, thanks to Nicholas, we get to spend time talking about the Carnot cycle. Isn't that great? Now the Carnot cycle, it's in your chapter. Let me see if I can find it here. It's on page 'Well, I thought the Carnot cycle was in this chapter, but I can't find it. Maybe, do you know what page it's on? Yeah, here we go. It's on page 156. Now, the Carnot cycle has 4 processes. It has 2 isotherms. And 2 adiabats. Now, you can have a Carnot cycle with ideal gases, and you can have a Carnot cycle with real gases that condense and liquefy. But whatever you have, you got two isotherms and two adiabats. Now, if you have an ideal gas, here's what the PV diagram will look like. There won't, if you have an ideal gas, there won't be any vapor dome. Quit putting vapor domes on ideal gases, you people out there. Quit it. You don't liquefy, it's a gas, it's an ideal gas. But if it has two isotherms, then here's how isotherms go. They go like that and like that. And there's a diagram of the Carnot cycle on page 160. On page 160. Here you go. Here's state one. And you have a isotherm. Yeah, there's state two. From 1 to 2. There you go. State 1, state 2. And then here's state 3. There's state 3. Now that was an isotherm. It followed the isotherm. That process followed the isotherm. But see, this one's the adiabat. And have I ever told you guys that adiabats are steeper than isotherms? Can you see that this adiabat is steeper? Let me write it for you. Adiabats are steeper than isotherms. I know I told you that before, but if I keep telling you stuff enough, it'll sink in. That's my theory. And then the Carnot cycle has another isotherm. So here goes 4. And there you go. There's state 4. That's a isotherm. It's got two isotherms. And then finally, back to where you started. See, it's a cycle. You're back to where you started. That's your other adiabat right there. See it? That's your other adiabat. And notice it's steeper than the isotherm. You can tell it's steeper. Yeah, it's steeper. So there's your Carnot cycle. Well, so what? Well, it's there are a lot of things we could learn about this cycle. And there's a problem dealing with it. I'd like to start working on it here if I can find it. This is chapter 5. Let me see if I can find the problem I want. Yeah, here we go. This is problem 549. Problem 549, it's air. Well, air can be treated as an ideal gas, so we'll just have air. And a piston cylinder goes through a Carnot cycle with a PV diagram shown in figure 521. Well, where the heck is 521? I don't know. Probably back in your chapter. Let me see if I can find it. There it is. I found it. You know what? It's just like ours. It's kind of like ours. Well, it's got two isotherms and two adiabats. Let me keep reading. If you just turned in, we're doing problem 549. It's a Carnot cycle. See, we've studied what? Heat pump cycles, heat engines or power cycles, and refrigeration cycle. Now, what kind of those three, what kind of cycle is this? Let me go to one of my excellent students here. I don't know if I picked on Taylor. Taylor, have I picked on you yet today?
Yes, sir.
I picked on Tyler. Tyler, I haven't talked to you yet today. Tyler, unmute and say hi, please.
Hello.
Hello. Tyler, this Carnot cycle is either a power cycle, or it's a refrigeration cycle, or it's a heat pump cycle. Which is it, Tyler?
Is it a power cycle?
Yay, good going. Good going, Tyler. It's a power cycle because, can you see it's clockwise? See, the other two are counterclockwise. Remember our diagram, our schematic? Okay, well, good. So what? Let me keep reading. The high and low temperatures are 600K and 300K. So let me write that down. This is 600K and this is 300K. The heat added at the high temperature is 250 kilojoules per kilogram. I like to do my heat added in red. It'll be right here. Here we go. The heat added at the high temperature is 250 kilojoules per kilogram. There isn't going to be any heat added on this adiabat. Now let me ask another wonderful student here. Reagan, you've been helpful today. I bet you can get this. Reagan, unmute and say hi.
Hi.
Hi. Now, Reagan, there's no heat added on this process from 2 to 3. How come there's no heat added on that, Reagan?
I think it's because there's no air circulation, or
That's not the answer the teacher wanted, Reagan.
I don't know. Today I'm kind of confused, Professor.
That's okay. That's okay. It's okay to be confused. Reagan, what's the name of this process from 2 to 3? What's the name of it?
From 3 to
It's got a name. It's written on here, Reagan. What is it? I'll give you a hint. It's steeper than the isotherms.
is diabet process.
Yes, it's an adiabat. Now, Reagan, what do you know about adiabats? You know something? What do you know about them?
Not really much. I'm trying to think hard.
Have you ever noticed when somebody asks you stuff, your mind just goes blank? Reagan, adiabats are by definition no heat transfer. That's what an adiabat is. So there's no heat transfer on that adiabat. There's no heat transfer on that adiabat. Did they tell us the heat transfer on this one? Let me read it. They didn't tell you. The lowest pressure in the cycle is 75 kilopascals. That's over here. 75 kilopascals. Now let's do our schematic that we learned how to do. This is a power cycle. So you want to draw what's the word? Clockwise. You want to draw clockwise. And you want to fill it all in. We did this before. I'm going to shut up and let you do it. I mean, I can sit here and do all this stuff, but you got to learn how to do it. I want you to draw the schematic. I want you to put in what goes in these boxes here, what goes here. On your mark, get set, go. Complete. I want you to complete and label the schematic. Draw and label. It's a power cycle. Draw and label the power cycle schematic. I'll be quiet. And then I'll pick on one of my best students here in just a minute. Well, I gave you a little bit of time there. Let me go to somebody. I think I've talked to all of those students already today. Let me find somebody that I haven't talked to yet. Let's see. Hey, Bryce, have I talked to you yet in this class?
Yeah, you did at the beginning.
Well, let's do it again, Bryce. Hey, Bryce, what do I put in this box right here?
600 Kelvin.
Yeah, good going. 600 Kelvin. I like it. What do I put in this box down here?
300 Kelvin.
Yeah, good going, Bryce. Now, is there anything else that we can? Oh, yeah, right here. Look here.
Mhm.
This is going to be either a little Q or a big Q. Need some room here. Or a little Q dot or a big Q dot. Now they gave us the number. It's 250 kilojoules per kilogram. But Bryce, which is it? Is it the little QH, the big QH, the little Q dot, or the big Q dot? Which of those is it, Bryce?
It's gonna be the little.
Which one? One of these is equal to 250 kilojoules per kilogram. Which one is it? Earth calling Bryce. Did I lose Bryce? I've got a bad feeling I've lost Bryce.
Always muted, so my bad. I'm saying little Q.
You're saying little Q?
Yeah, little QH. My bad.
You're right. Good going, Bryce. Proud of you. It's little QH is, if you can read my writing, is 250. See, you can tell by the units. You can tell by the units. Kilojoules per kilogram. That's a little Q, isn't it? Okay. Now here's what we're going to do. We got 9 minutes left. Isn't this great? We got 9 minutes left. I just need some room here. What we're going to do is a Carnot cycle is a reversible cycle. It runs perfect. That's why there are no real world Carnot engines out there. You won't see a car go by that's running on a Carnot engine because you don't get perfect efficiency. Cars don't get anywhere near 100% efficiency. There are no Carnot engines in existence, but there are in theory. This is a theoretical thermodynamic cycle. And what we're going to do is we're going to set the efficiency actual equal to the efficiency maximum possible. Now, we've done this before, and we can do it again. Now, the actual efficiency is going to be, it's going to be the little w divided by the QH minus the QL. Well, the thing is, we know what the QH is. No, just a minute now. Yeah, there we go. That's the QH. It's a little w over the QH. Now the theoretical, here we could write this like this. The 250 minus QL. There we go. Now there's your actual efficiency. And here is the theoretical efficiency. That is 600 minus 300 over 600. Here's your equation. We're going to solve for QL. I'm going to shut up for 1 minute. Solve for QL. Go for it. We've called on just about everybody today. Let me go back to my friend Alex. Alex, unmute and tell everybody what that little QL is.
I got 125 kilojoules per kilogram.
That's what I got. That's what I got. Well, let's draw it on here. Look here. There's a heat transfer per mass coming in. And there's a heat transfer per mass going out. There it is. Does that show up? Yeah, that shows up. So you got 250 coming in and 125 coming out. Here, let's draw them on here. This is little Q, L, it's 125. So now we can get little W. Now, if you have 250 coming in and 125 going out, what is little w? Well, it has to be 125. Does that make sense? Think about it. 250 comes in, 125 comes out, 125 comes out. They add up. This is your work per mass. We've got our work per mass on our Carnot cycle. And what would be the efficiency? You tell me. What do you think?
50%.
Yeah, it's 50%. 50%, or you could just say 0.5, that'd be fine. So we've come a long way. And we know this.
So perfect efficiency is 50%?
At those temperatures.
Okay.
At those temperatures, the best you could ever get is 50%. See, the efficiency depends on the temperatures. Does that make sense? That's why they're thinking of some airplane engines to operate way up high above the clouds in the stratosphere. It's very cold up there. It's very cold up there. And so you get a big number here in the numerator. See, this number here is 600. Well, if you can make this colder, see, it's 300, right? Well, what if it was 200? Or what if it was 0? Well, you're not going to get 0. That's outer space. But if you had a smaller temperature, and that's what they're working on for some airplanes flying way above the clouds, you could get a very large efficiency, plus less danger. See, the danger with flying through clouds is you get hit by lightning and you get turned upside down by the storm. Well, we're gonna do some more with the Carnot cycle on what is today? Wednesday? Yeah, Monday. Do your homework. And it is time to end though. I think we finally run out of time. That was fun. Did anybody have any last things to say before we say goodbye?
Yes, sir. This is Taylor. In
Taylor.
the question we did, 549, it says to find the specific volume and pressure.
Yes.
So how would we go about finding the specific volume after we know from where we're at? Just if you could detail with the steps.
Taylor, I'm going to show you how to do that. Of course, you can find the specific volume at state 3 with no sweat, because at state 3, P3 is given 75 kilopascals. T3 is given, it's 300 K. It's an ideal gas. So P3V3 is equal to RT3. And we know T3, we know R, and we know P3. So you can get the specific volume at state 3. And then I can show you how to get the rest. But we're out of time right now. It's sad.
That was really what I was looking for, so thank you.
Yeah, anytime. Anybody else?
Yes, I do have, this is Reagan.
Yeah.
I was looking on my exam, my test grade. I
Yeah.
didn't get any feedback on that. Like, I don't know what exactly I did wrong.
Okay, Reagan, I can tell you. Email me and I'll email you back and tell you where you went wrong, okay?
All right, I'll do that.
Yeah. Anybody else? Okay, well, bye-bye for now, students. I'll see you next Monday at 11. Yeah. Adios, muchachos.
Bye.
Hi, Mr. Griffin.
Bye-bye. Be careful out there.